Okay, welcome, Victor and Ralph and Jordan and Jacob. Hopefully we'll have a few more too. So this is actually the second meeting. And let me go over the agenda for the day. Okay, so the plan today, we have actually a lot of things to do, but none of them are very hard. That's the good news. First thing is I'll answer questions. That could be hard, who knows? And then after that, we'll define what it means to be a homogeneous system, kind of a scary sounding, long word, and it's easy, trust me. Then we'll talk about what it means to be a trivial solution and what it means to be a non-trivial solution. Also, no big deal at all. And then we'll get into linear combination. And then we'll talk about the rank of a matrix. And then we'll look at the rank, the parameters, and uniqueness of solutions. And then we'll do some applications. So we'll balance chemical equations. Let me ask you guys, put a yes, say yes if you have had chemistry, no if you have not had chemistry or if you're in it now. In it now. Okay, Caesar, you're going to be happy. Okay, although if you had it last quarter, it's too late. And you're still in it now. Okay, so it turns out there's a much easier way to balance chemical equations than the way you typically learn in the chemistry class. But do you know why Sean didn't teach you the simple way, the easier way?
Because this isn't a requirement for that class.
Exactly. He can't say, oh, everyone knows linear algebra. But it's really easy, especially if you have a computer. It's really simple. And we'll see why it's simple. Nice and simple. So then we'll get into circuit analysis. And let me ask you again, because I don't exactly know what your backgrounds are. If you've had any physics that included circuits, put a yes. If you've never done any physics with circuits, put a no. Okay, so we're seeing a lot of yeses. Okay, so we're going to do circuits, and we're going to keep them somewhat simple, and not because I don't want to get difficult ones, but because I don't want to spend all day writing long numbers and matrices and things like that are 10 by 10. But with a computer, you can, and it's no big deal. It just takes a lot of typing. So it turns out that if you have linear algebra and you have matrices, solving circuits, especially certain types of circuits, very simple. There is a kind of circuit that we're not going to do, the LRC circuit. And the reason is with capacitance. Did you talk about capacitance in your class? Capacitors? Yeah, to solve a full circuit when there's a capacitor involved, you need next quarter's math, actually. So you need differential equations. And so we can't do that, but we'll do non-capacitor type circuits. Okay, so just LR circuits instead of LRC circuits. And we'll see, I'll give you one example. Then we'll talk about equivalent matrices. So when are matrices called equivalent? And then we're gonna do arithmetic. Sounds easy? It is. Okay. The arithmetic we're gonna do is easy. You may notice that I'm gonna do A plus B, and maybe I should write A minus B also, because those kind of go together. A minus B. So we'll go to how do you add two matrices? How do you subtract two matrices? And the answer is easy, no big deal. Then we'll get into how to multiply matrices. That's a little harder. Okay, it's a little harder, and it is not something that you would guess just by, as your first guess on how to multiply matrices. It's not hard as in once you know how to do it, it's no big deal. It's just you have to learn how to do it, and you have to realize it's not what you expect to do. Then what we're going to do is we're going to talk about A transpose. So how do you take the transpose of a matrix? And the nice thing is that's also very, very easy. All right, I got a tough question for you right now. There's 12 items on the list. Okay, and we're not going to count number 1 because you never know what number 1 is. Of 2 through 12, which is going to be the most important on the list that we're going to do over and over and over again and
4.
hard?
Number 4.
Number 4. How'd you guess?
I got a different textbook before the class started, and I was reading it, and it just shows up the whole time.
Yeah. Okay, so you've read the whole textbook.
Not quite, just peeked through.
Which is fine, by the way. In fact, when I was a student, that's what I did over break. I read the whole textbook of all my classes that I was about to take. And that way, you know, I had a head start on everything and I did well. So nothing wrong with reading ahead of time. It turns out linear combination is basically in the top 3 of all things we do in this entire class, just to let you know. That doesn't mean you don't have to know all the rest of it, but linear combination is, it's a biggie, and not just with matrices, it turns out, as we'll get into. This class is not all matrices, by the way. It has some other stuff involved. But today and Wednesday was all matrices. So any questions at all about anything? That could be a homework problem. It could be something that about the class. Any questions?
Yeah, could we get like in the future homework assignments to be due just a little bit into class, just in case we do have any questions on the homework problems?
I'll tell you what. Here's the deal. I believe they're assigned at a certain time, but you can turn them late. It just says they're late, right?
Yes, I think
so. Here's the deal. If you log in and be in class, whatever that means with Zoom, but if you're logged into Zoom, then I'll allow you to turn it in late up to, how about a half an hour after class without penalty. If you're not logged in, absolutely not. Because what I don't want, so here's what I don't want. I don't want people to say, you know, I really got to get this homework done, so I don't have time to go to class. Because that's just a bad habit and it'll bite you. So that's why I want to make sure that there's a reason why class is important. Does that make sense? Does that sound like a fair?
That makes sense. Yeah, it sounds perfectly fair. Yeah.
Yeah. So it'll still say late. Late does not necessarily mean you'll lose points, but if you didn't log in, and there's only 9 of you, I can remember who logged in. Okay. So if you didn't log in, then it truly is due at 1. But if you did log in, I'll give you till 3:15.
Sounds perfect. Yeah.
Okay. And log in means you have to participate the whole time too. Okay.
Yeah.
So if I, hey, if I ask you, have you had circuits and you didn't answer, that means even if you're logged in, that doesn't count because that's not a hard question. Does that sound fair? You have to log in.
Definitely.
You have to participate. It doesn't mean you have to answer correctly, but you have to participate. Okay, sound fair? Okay, yeah, because I just want to make sure that, we have a way, because in regular class, what would happen is you'd be there and then you'd turn it in after I was done answering questions. Do you remember that? It's been a long time since we had like a regular, like sitting in a classroom class.
Yeah, vaguely. Like we would have a bit of a question thing, and then like we could ask questions from the online homework up through Canvas, and then finish off those answers with yeah.
With Zoom, it's much harder to come up with like a good way of doing it. So it sounds like a way of doing it. Any other questions? Now that you know the rule, any questions about the homework? No questions. Okay, if there's no questions, then we'll get into, we have a whole lot of definitions today. Today's like definition day. But the good news is none of them are hard. I think you'll agree. Is there still an incentive for completing all the homework? There is officially, And that is, you don't get to drop a test. There's only 2 tests. And I'm trying to make it more realistic to, university. So they don't drop tests, by the way. So I allow, that means that on your honor, if you do all your homework, you get to use a 3x5 note card. Okay. Honestly, I won't know the difference, but try not to, it's better not to cheat. Then you can be honest and you can feel good about yourself and know that you actually passed honestly, which is the right way to do it. And so that's my incentive there. Sound fair? Okay, any other questions? Okay, if there's no questions, let's get into some big definitions. They're all important, by the way. So you have to know them all. So I have them written out. I recommend taking notes as we go through this. And there's a lot to talk about. So I actually typed it out ahead of time. So let's start out with the first big definition. And that is what's called a homogeneous system. Again, scary sounding word, but really is no big deal. So the definition is a homogeneous system of equations is a system where there are no non-zero constants without variables. Okay, in other words, the zero vector is a solution. Okay, so a system of equations is homogeneous if and only if the zero vector is a solution in linear algebra, by the way. In linear algebra. So that means, by the way, do you guys know what linear is? I probably should have mentioned that Wednesday, but
relating to lines.
It's got relationships to lines, but the problem is, remember, we could have 100 variables. Okay?
Variable.
So a plane, for example, is linear.
It can be square or to a power.
Okay,
Yeah.
you can't
greater than 1.
You can't have a power. I'm not even going to say greater than 1. I'm going to say other than 1 or 0, because 0 power is constants. Because you can't have a half power, and that's not greater than 1. Does that make sense? But that's not enough, because cosine of x is not linear. And that's not a power. So you get in trouble if you just jump to powers. So I think that because calculus is a prereq, although I did say we're not doing calculus, we're not doing much calculus. What it means is that the partial derivative with respect to every variable for each equation is a constant. So that's a definition. There's a lot of ways of defining what linear means. So if you take the partial derivative with respect to x, y, and z, for example, if there's 3 variables of each of the equations, you get a number. Nothing with x's, nothing with y's, and nothing with z's. And that makes it linear. Okay. The other way of defining it, we haven't learned yet. And that has to do with matrices, actually. That means it can be written as a matrix equation. But we're not quite there yet in terms of matrix equations. That's, I believe, next time. So here's an example. And that is x plus y plus z equals 0. And 2x minus y plus z equals 0. Do you agree that is a linear system of 2 equations? If you take a partial derivative with respect to x, y, or z, in the first one, you always get 1. In the second one, you get 2, -1, and 1. All numbers. No x's, y's, or z's in them. Now it's homogeneous because you'll notice there aren't any constants without variables here. Okay, non-zero. 0 is allowed. Okay, in fact, you're going to have to, typically you'll have a 0, but you don't have to. And that makes it a homogeneous system of equations. Any questions on that? Okay, also notice that if you plug in 0, 0, 0, the 0 vector, does it work? Yeah. Okay. By the way, was my promise correct? This is pretty easy. Okay, hopefully, because it's not supposed to be hard. But here's what I'll tell you. When you have a homogeneous happens all the time. So when you have a homogeneous system of equations and you want to write the matrix form, you pretty much never put the line with the column of in this case, it always would be zeros. So below is the matrix expression for this homogeneous system. Whereas Wednesday, we would have had a column, a fourth column that was 0, 0. But if it's a homogeneous system, it's implied. And it turns out that's going to work a whole lot better for us with matrix theory. So the matrix that corresponds to this homogeneous system is 1, 1, 1, 2, negative 1, 1. Okay, we don't say it's an augmented matrix. We just say it's the matrix. And if you have a matrix and you say, hey, this represents a system of equations, it's implied that you get equal zeros. Okay. Any questions at all on this?
That's always the case, right? It's implied that you have equal zeros.
If it's homogeneous, if you're told it's homogeneous. Yeah. If you're thinking of it as a system of equations and you have a homogeneous, by the way, do matrices always represent system of equations like this?
Since you're asking, I'm going to guess no.
Yeah, the answer is no. And you've already seen them when they didn't. When is that? Not in my class. That would have been 2 days ago.
Cross product with vectors.
Yeah, cross product with vectors is one example. There's another one that happened. Starts with a J.
Jacobians.
Yeah, Jacobians. Jacobians are really important. And they're going to be the reason why we do a lot of what we do, is because of these Jacobians. Okay, Jacobians are really important in terms of all kinds of physics, okay, and engineering. And that's a matrix. It's not a system of equations. It's a matrix that represents the partial derivatives of evaluated at a point, right? Which is what the Jacobian is, okay, or not evaluated at a point. And then you're going to have a matrix not of numbers, but of functions. Okay, the cross product, you're right. The cross product is also an example, but really you just use that because it's like convenient. And that's about the only reason why I use a matrix for that. But Jacobians, you need it as a matrix. Any questions on this example of a homogeneous system of differential equations? I mean, sorry, of linear equations. Okay. So homogeneous systems are important. And in fact, next quarter, I keep doing that to you. I keep saying next quarter. Next quarter, you're going to take differential equations. My guess is probably maybe all of you are going to take it. Is that true? Okay, not a whole lot of people take linear algebra and then don't move on and take the next quarter. You don't even have to pass this class to take next quarter, but you want to pass this class. And it turns out step one in next quarter for most of the problems next quarter is to take all the things to the right and just make them zero and then solve the homogeneous system. Just let you know that. So that's tend to be step one. So you have to be able to do homogeneous systems next quarter in a big, deep way. I'm not going to get into that because that's Bruce's job, because he'll be teaching the next quarter's class. Okay, any questions at all on homogeneous? No big deal? Okay. So a couple very basic definitions. The first is that the zero vector, as I mentioned, is always a solution, right? It's kind of part of the definition. Since it's always a solution, you don't usually like call it out, right? If something's always true, you don't need to mention it. And when you don't need to call something out because it's always true, the English word you use is trivial. So the zero vector is called the trivial solution to a homogeneous system. Okay. You may feel good that you found a solution, 0, 0, 0, 0. There it is. It worked, right? You didn't have to do any work and get that solution, but it was trivial. Every other solution is called non-trivial. Any questions on that definition? Okay, so 0, 0, 0, 0 is definitely the trivial solution. Anything else is non-trivial. For this particular system, are there non-trivial solutions?
Yes.
Yeah, the answer is yes. Yeah, definitely yes. And in fact, without finding the solutions, you can get that yes at a glance. Okay, the yes is not the same thing as I know what the solutions are, but I know there must be more solutions. And thinking about it as equations, and then we'll get into matrices also. How many equations are there?
2.
How many unknowns?
3.
3.
3. So when it's homogeneous, and when you have fewer equations than you have unknowns, how many solutions do you have?
2.
Nope. More than 2. That's a hint.
Infinitely many.
Yeah, an infinite number of solutions. So there's going to be an infinite number of solutions to this. Okay, and one way of thinking about this is these are both planes, right? Let's think geometrically for a moment. These are both planes. X plus y plus z is 0 is a plane. You were supposed to have learned that last quarter, right? And 2x minus y plus z is also a plane. And how do we know they intersect?
Because they're not parallel.
Yeah, but there's a really easy.
Oh, yeah, they equal 0. So
yeah,
they must
because they
intersect
intersect at the origin. Yeah, they intersect at the origin. Any homogeneous, because whenever you have a homogeneous system, it always intersects at the origin because that's what it means, right? And if you have two planes that intersect, then what must they intersect in? In a word?
A vector or a line, I think.
A line, right? Two intersecting planes always intersect in a line, right? Basic geometry, right? Hopefully you know that just from looking at your, in fact, you can look at your ceiling and your wall. How's that? And you can see they intersect in a line. And this is always going to be true, no matter where you're sitting. Some of you don't even have your webcams on, but I know that your ceiling and wall intersect in a line. Okay? Unless you have some very weird architecture, as long as they're all linear. So we know that there's an infinite number of solutions. So there's one trivial solution, always will be one, but there's an infinite number of non-trivial solutions to this. Any questions on that? How do we find the non-trivial solutions, all of them, for this system, especially now that I've made it as a matrix?
RREF it.
Yep, RREF, which in this case is easy, okay, or pretty easy. So let's do that because it's good practice. What I recommend doing, by the way, if I say let's RREF, try and do it by hand before I do it because it should take me longer to type than for you to write on paper. Paper's a lot easier. Whoops, it didn't copy. Copy, paste, good. Okay, so I'm going to take negative 2 times row 1, add it to row 2 to get that 2 to be a 0. Get that negative 1 to be a negative 3. And that 1 becomes a negative 1. Any questions on the first step in our REF? Okay, let's divide or multiply negative 1/3 times the second row. And when we do that, that negative 3 becomes 1. That's the whole point. And the negative 1 becomes positive 1/3. And then what I need to do is I need to take row 1 and replace it with row 1 minus row 2 to get rid of the 1 above the pivot. And when I do that, that 1 becomes a 0. That's the whole point. And this 1 becomes a 2/3. Any questions so far? Okay, is this RREF'd?
Yes.
Yes. And what that means is we're ready to write down the solution. Okay, what are the free variables? Or variables?
X, Y, and Z.
Not quite.
Z.
Z. Z is a free variable. What are X and Y called? Start with the P.
Are pivot positions?
Yeah, those are pivots, right? So we have pivots in the X and Y column, and we have a free variable in the Z column. So it's a review from a couple days ago. Do you remember that?
Yes, now I do.
Okay, so that means since Z is the free variable, that's going to be our parameter. How about T? Because that's usually when you do parametric equations, you use T. So now we can write it in parametric form, and we can say X is equal to negative 2/3 T. Y is equal to negative 1/3 T. And Z, what's Z equal to?
T.
T. That's our free variable. The free variable is the parameter.
Why are they negative again? The negative. Why is it negative 2/3 and negative 1/3?
Okay, so let's go back to the original and see the equal 0.
Uh-huh.
There's a hidden equal 0. So this says X plus 2/3 Z equals 0.
Oh, okay.
And then I subtracted 2/3 Z from both sides. So
Okay.
sometimes I'll do things in my head, and I apologize if you're not following my head. But that's one I'll usually do in my head, is the free variables become negative because they get pushed over to the other side of the equal sign, the hidden equal sign in this case. Any questions at all on this? So for example, notice, by the way, 0, 0, 0, 0 is definitely a solution. It's always good to double check. That better be true, right? But I don't know, let's let T equal 3 because it's prettier. And we can say, for example, that if T is 3, you get negative 2, comma, negative 1, comma 3. That's a non-trivial solution. Anyone lost on that idea? So I just found one non-trivial solution. Is there another one?
Yeah, there's infinitely many. So
Right. You give me a T, I'll give you a different one. Do you see? I'll give you a new one. So I let T be 3. You could let T be 10. You could let T be pi, whatever you want. And there's an infinite number of choices for T, which means there's an infinite number of non-trivial solutions. But there's only one trivial solution, period, always. Any questions at all on this idea? Okay, so let's move on to next definition. So we've got trivial, non-trivial. Now we're into linear combinations. Okay, please take notes on this one. Write it down 100 times. You have to know this by heart. And that says the following. Okay, I do it a little differently than the book. And the reason why I do it a little differently than the book is when I redo it, I don't have to change anything. Whereas the book has to change their notation. And I like to give you the notation that we're going to use for the whole class, instead of say, well, this week we're using this notation, next week we'll use a different notation. So let's suppose that V1, V2, ... Vk are vectors. Okay. By the way, today, a vector is a list of numbers in order, right? It's a list of numbers. Isn't that true? Okay. What was the first word I said?
Today.
Today. Any guess on what that means?
That might change on Monday.
Yeah, not Monday, but in a few weeks it will change. Okay, so just note that these vectors for now, that's just fine to think of them as vectors that you had in last quarter. Okay, not a problem at all. On the other hand, we're going to change that later on. And in fact, Caesar, you're a vector. You may not realize, but you're a vector. I could define you as a vector. Okay, Bradley, I could define you as a vector also. And you're different vectors, and I can add you guys up. Okay, now that sounds weird, but if you do it right, you can make just about anything a vector. Is a matrix a vector? Yep, definitely. Okay, so later in this course, we're going to have a more abstract definition of vectors. So I want to give you a heads up so that you don't get it like pressed in your mind that a vector always is just a list of numbers. It just is going to be for this week. Okay, and I think next week too, and then it changes. Okay, so a linear combination of these vectors is a vector in the form, and I like to write summation notation to remind you that's what's going on. The book doesn't, but that's what's happening. It's a summation from I equals 1 to k of CIVI. Okay, which is, if you don't write it in summation notation, if you write it in ... notation, that's the same as C1V1 plus C2V2 plus ... plus CKVK. Where C1 through CK, they're not, in fact, I'm going to make sure it's constants, but let's change that constants to scalars. ORS? No, ARS. Okay, do you remember what a scalar is?
It's like a multiple, right? That you multiply a vector by in order to.
Yeah, kind of an easier way of saying it is number.
Oh, okay.
A scalar is a number. You can say multiple, but I think number is a nice, easier way because you could tell a second grader that, and they get that it's what a number is. A scalar is a number, whereas a vector is different because a vector is, at least for you guys now, is a collection of numbers. Do you see that? And then later on, cosine of x is a vector. You don't believe me, but it is. So there's all kinds of weird types of vectors. But scalars are always just numbers. And in our class, and that might change when you get into upper division, our class, our scalars are going to be real numbers. So we're not going to get into complex numbers. Next quarter, you do some of that. But we keep it simple in this class. There might be, I'm trying to think, there might be one time when you do complex numbers, but not much. So we're thinking of these scalars as real numbers, but you can move it on to complex numbers.
I have a quick
or if you
question
get,
for
yeah.
you.
Mhm.
Do you put these notes on Canvas?
What I do is I put the video on Canvas.
Okay.
So you've got it. I don't do it in writing. In fact, the last one I already erased it because I use the same Word document. I mean, I guess I can if you want, but the video's up there.
No, that's good. Thank you.
Yeah, I put it on
video's up
Zoom
there.
and then I embed the Zoom into Canvas. Did you notice that for Mondays? I don't know if anyone looked at it. Yeah, so it's there, and I have a playlist in YouTube. So you can go to that YouTube playlist and you can look at all of the different lectures. So far, we only have one, but eventually there'll be a whole lot more. Does that make sense? And the cool thing is next year, when we have a snow day, I can just tell them to watch the lecture because it's already happened. Snow days don't happen when we're in COVID times. Any questions on linear combinations? Okay, so it's easy to talk about them. Let's suppose we have, I don't know, let's write one out. I don't need equation. I think I just write it as V is equal to, I hate that it auto capitalizes. There we go. is equal to, how about 2 comma 4 comma 1? W is equal to 0 comma 5 comma -2. Just making some numbers up. Okay. By the way, I didn't write it out in the definition explicitly, but the vectors must be in the same universe. So V1, if it's 3-dimensional, V2 also has to be 3-dimensional. Does that sound fair? Okay. I didn't write that, but that's true. Otherwise, it doesn't even make sense. And you should have gotten that last quarter and even third quarter calc. So I can even say it's a prereq. It doesn't even make sense to add vectors if one's in R2 and one's in R5. Is that clear? And when we get more abstract, it still wouldn't make sense to add, this universe versus this other universe and add them together. So these are good because they're both 3-dimensional. And I don't know, how about let's get another, how about P? I'm just making up another letter. P equals 2 comma 1 comma -1. Then we could look at, how about V plus 2W plus 3P. Okay, is that a linear combination? What do you think? Is that a linear?
Yes.
Yeah.
Yeah.
By definition, it is, because it's a constant times V plus a constant times W plus a constant times P. So it's a linear combination. Okay. So now this should be busy work, the hope, unless you're totally lost. See if you can get, I'll give you 5 seconds. It shouldn't take longer than that. Okay, what'd you get for the first coordinate? What number?
1. Oh, oops.
Okay, I think I better do it because I'm hearing wrong numbers. Okay, so we have V, there's a 2 there. We have 2 times 0, 2 plus 2 times 0 is still 2. And then we have 3 times 2 is 6. And we get 8. Anyone lost on that? Wasn't supposed to be hard. This is not a trick question. Okay, and then the second coordinate. Okay, so I guess I should do it in my head quickly. So we have 2 plus 10 is 12 plus
17.
Wait, let's try again.
Oh,
2
wait.
plus 10 is 12.
Okay,
Plus
15.
3 is 15. So I'm not sure if you're not understanding or if you're just making arithmetic dumb mistakes. What is it? Does everyone understand how I got 15?
Yes, now I do.
Okay, because I'm seeing different numbers. So the question is that because you just made a little stupid arithmetic error, or is it because you're lost on what it means? Okay, and now the third coordinate, let's see if you can do that. A little arithmetic, nothing too hard. This one's got negatives though. Good, -6. By the way, let's not do it, but I want to ask you, what if I just said, how about 2V minus 5P? Is that a linear combination of VW and P?
No, because it doesn't have 3 dimensions.
Okay, one more guess.
Yes, it is.
Yes, because it's 2V, a little hidden here, plus 0W. Is 0 a number? Is a scalar? Yeah. Plus -5 times P. Do you see? So yeah, that's also a linear combination. You're allowed to have zeros. And in fact, the 0 vector is always a linear combination of whatever you give me. Do you see that? because you can make all the coefficients 0. Any questions at all on this definition of linear combination? Okay, now comes something very important, and I'm writing it as fact. Do you know what fact means in math? No?
Something that's provable?
Yeah, it's something that's true, but I'm not ready to prove it for you guys yet because you need some more math. So I'm not going to call it a theorem yet because I'm not proving it today. Eventually it'll be called a theorem. So I'm calling it a fact for now, just because, yes, it's true, but it's one of those that's true, but you got to trust me. Okay, and that is if V1 through VK are solutions to a homogeneous system, then any linear combination of these vectors is a solution also. Okay, that's a really important theorem. But you have to understand like full matrix arithmetic to be able to prove it. And we're not there yet. Okay, at least to prove it nicely. And then it's really simple. So this is a biggie. So that means that if you got a couple solutions, already you have an infinite number of solutions. If you have even one non-trivial, you have an infinite number of solutions because any constant times it is going to be a solution. Any questions on the fact? Okay, next definition. Again, a lot of definitions today. Let A be a matrix and consider any row echelon form of A. Do y'all remember what row echelon means? That happened 2 days ago?
It's like reduced form row echelon, except there can be numbers surrounding the pivots. Well, except for the first pivot, there can't be something in front of it.
Okay, not quite surrounding. You could have numbers above, but not below.
Okay.
Yeah. So RREF means that you can't have numbers. You could have numbers, but the numbers all better be 0. RREF means that you have zeros above and below the pivots. REF means you have zeros below the pivots. And the pivots have to be 1s. Okay. So let's suppose that we're looking at any row echelon form of A. Then the number R of leading entries of A does not depend on the row echelon form you choose. Okay. And we call this the rank of A. Okay, very important word for a matrix. So really important to know what the rank of the matrix is. And typically you write it as rank parenthesis A and parenthesis. And that's the rank of A. Okay, and we know from last time that the rank is well defined. Do you guys know what well defined is? Do you know what that means in math? Any of you know?
It's widely understood that that's what it means.
Not quite. Okay, it means that if there's two things, they must be the same. So notice this word any. Okay, there are a lot of different row echelon forms of A. But no matter which one you look at, you're always going to have the same number of leading elements. The same number of pivots is another word, by the way. So you're always going to have the same number of pivots, no matter what row echelon form you're looking at. The rank is always the same. Okay, whereas if you have different, different values for different row echelon forms of the same matrix, then the rank wouldn't be well defined, and it's not a good definition at all. So well defined means no matter how you look at it, you always get the same for a given matrix in this case. Any questions on this definition? So the rank, let's write this out. The ranks is the number of pivots. Okay, which is the same thing as a leading number of leading entries. So the rank is the number of pivots of a matrix. You REF, if you want to RREF, you can do that too. And then you find the number of pivots. Okay, so I have a job for you. I want to see if you could do it. And I want you to use technology. I want you to go on a computer. And here's a matrix, 2, 1, 1, 3, negative 1, 2, 7, 1, 4. I don't want you to do this by hand. Okay, it is important to know how to use technology. And get online. There are a lot of technology platforms that will find the REF, because that's what you got to find. Find the reduced echelon form of this matrix. And if you don't have your favorite one, I like Symbolab. That works pretty well. And in fact, if you just go to Google and you type in, REF matrix, Symbolab, at least for me, it came first. Click it and it'll give you, it'll set you up. Let's see if you can do that. I want to give you a minute or two and then I'll do it, but I want you to try it. Because it is important you know how to use technology. Good luck finding a job if you can't use technology in STEM. Okay, what system did you use? What technology you use? A random calculator. Okay. Online. Wonder what that was one. I bet it wasn't completely random.
I just use Symbolab.
Symbolab, this is Math ODU. I don't know that one. It worked. That's the important thing. And you REF'd it. Is everyone good? So what'd you get? I might as well put it in. I can't REF this one in my head without spending a lot of time. I can, but it would take too much time. So what'd you get for the first row? My guess is you'll have the same answer with this one. I don't see you jumping in. 1 0 3/5. Yeah, I purposely made it so it was going to be fractions because I wanted to use technology, and so I wanted to be kind of messy. Okay, what'd you get for the second row? That's a 0 for sure. 0 1 negative 1/5. Okay, now I know the third row without you telling me because you told me it is of rank 2. So the third row must all be zeros. Because if it wasn't, you have a pivot. So I don't need technology to know that. I need to know the rank was 2. Okay, so then we know the rank is 2. Any questions on the rank? Okay. So here's a theorem. Let's suppose A is the m by n coefficient matrix corresponding to a homogeneous system of equations. Okay, kind of like what I did at the beginning. We had a system of equations over here that was homogeneous. Then we looked at the matrix right here. In this case, it's a 2 by 3 matrix. So allow me to continue on the theorem. So if we have a homogeneous system of equations, okay, and suppose A has rank R, then the solution to the corresponding system has n minus R parameters. We really proved that last time. Do you remember? We just didn't have the word rank. But we said take the number of pivots, and everything that isn't a pivot is a parameter. So that's the proof. So if you want to find out if you have a homogeneous system, then just take n minus R, and that's how many parameters you have. You could also say the dimension, the geometric dimension of the solution is n minus R. And because n might be big, and R could be, not even that big, you may not even have a word for what the geometry is, What do you call a 9-dimensional linear thing? Good luck.
And n represents which dimension of the matrix? It's like...
So take a look. We have an m by n. So do you remember when you do m by n, m always corresponds to the number of rows, and n corresponds to the number of columns. So it's a very good question and very important, because we're going to be using this the entire quarter. So that means if we have n columns and the rank is R, then we'll have n minus R parameters. Okay. By the way, can you have if you have, say, 3 columns, let's say you had a 10 by 3 matrix, can you have the rank be 5?
No, because ranks can't be negative, can they?
Yeah, you can't have a negative number of parameters. Not ranks. Parameters can't be negative, right? Hopefully, Bruce didn't give you a parametric form of something with a negative number of parameters. It doesn't even make sense, does it?
Yeah, it doesn't make any sense.
Yeah. So you can't have a rank that's bigger than the number of columns. Okay, that's a corollary to this theorem. Any questions on that? Okay. And that's obvious when you think about it, because remember, you go to the pivots move from left to right. And if you only have, 10 places, 10 columns, then you can't have more than 10 things as you move from left to right, because you don't have anywhere else to move after 10. Okay, the next one is let A be an m by n augmented matrix. So now it's augmented. So now we're actually talking about that line with the numbers on the other side, corresponding to a consistent system of equations, okay, in n variables. And suppose A has rank R. Are you following what all these words mean so far? Okay, then the system has a unique solution if R equals n. And the system has infinitely many solutions if R is less than n. Why is that obvious? If R is less than n, what do you know about parameters? Take a look at n minus R. What do you know about n minus R?
N minus R defines the amount of parameters.
Yeah, but in particular, what's the smallest it could be?
0.
It can't be 0 if R is less than n.
Oh, 1 then?
1. You can have at least a parameter. As soon as you have a parameter, you have an infinite number of solutions, because a parameter could be any number. Do you see that? So
Yeah.
Number 2 should be obvious, because if you have a parameter, you have to have an infinite number of solutions. Number 1's not quite as obvious. We're going to prove that one later. Again, there's some stuff that we don't know yet, and that's inverses. And we'll get that, and then it'll be a really clear proof and easy. Okay, so again, you can REF a matrix, you can count your parameters by looking at n minus r. And if you have one, you have an infinite number of solutions. As long as you have at least one, you must have infinite. Okay. On the other hand, if r equals n, then it didn't work. And r can never be greater than n, remember? So there is no number 3. Any questions in this theorem? Okay. Now comes some applications. Okay, so here is an example. I want to put space. I don't want you to all look at the answers. All right. So I want to tell you how I found this example. I went online. I love the internet. And I typed in a Google search, really difficult balancing equations chemistry. And it gave me a worksheet, and it had a list of like 10, and there were 2 of them that were like triple starred, as in these are tough. So you've all seen this before. You all said you've had chemistry or in chemistry. Hopefully you can read this. CU, do you remember what CU stand for?
Copper.
Copper. Okay. I don't know why I say U though. Copper is COPPER. You must have come from something. Okay, so copper plus a hydrogen nitrate, and that, you know, if you throw it in a fire, you're going to end up with copper nitrate plus nitrous oxide plus water. Okay. Now you have learned how to balance equations, right? In chemistry, but you probably didn't learn the way I'm going to show you. And there's a really easy way to balance equations. Don't get mad at your teacher. If you had Sean, don't get mad at Sean because he didn't show you the easy way. But there's a really easy way, especially if you're allowed a computer. So what you do is the first thing is you write down variables, and I'm just going to choose A, B, C, D, and E for the variables. And by the way, I could get away with D. D is an awful variable last quarter, right? But I can get away with it. Remember I told you about calculus. You don't really need calculus in this class. So I can let D be a variable. I could let E be a variable. Those are letters you avoid, you know, in calculus for sure, but we don't have to worry about that. So I'm just going to make it easy. A, B, C, D, E. You can call it X1, X2, X3, X4, and X5 if you want. It's more typing. And then what I'm going to do is I am going to write down a system of equations based on each element. Does that make sense? So I'm just going to go in order. Let's start with copper. Well, with copper, the coefficient here is an A. Here we have a C, but it's on the right-hand side, so it gets moved over as a negative C. So we get A minus C equals 0. You following that? All right, now let's go to the next element. Now it's hydrogen. So hydrogen, I have a B in front of this hydrogen here. And then there's an E, but it's a 2E because we have an H2. And since it's on the right, you got to move it to the left by making it B minus 2E equals 0. Anyone lost on what I've done so far? Okay, and then I just go to the next one, nitrogen. So for nitrogen, I have a B, and then I have a minus C, 2C, because if it's on the right, it gets moved as a negative on the left. And then I have a minus D and no E's. So B minus 2C minus D equals 0. You following? Okay, then I go to oxygen, our last element here. So I'm going to have 3 B's, and then I'm going to have a minus 6 C's. And then I'm going to have a minus, oh, did I make a mistake here? Let's see, we're an oxygen, yeah, minus E, that's right. So we're going to have a minus D and a minus E equals 0. Any questions on how I came up with the equations? Okay, do we have a system of equations, a system of linear equations? Yeah. Let me ask you something. Will this always work in chemistry?
Yeah.
Yes.
Yes, this will work no matter how miserable the balancing that you have to do is. This always works. It's foolproof. So then I could take the system, I could turn it into a matrix, and I look at the coefficients. So remember, I do it alphabetical because it's life is easy if it's alphabetical. So I get 1a, 0b, negative 1c, 0d, 0e. So 1, 0, 1, negative 1, 0, 0. And then I do 0a, 1b, couple zeros for C and D, and a negative 2 for E. 0, 1, 0, 0, negative 1. And then I do 0, 1, negative 2, negative 1, 0 for the next row. And then 0, 3, negative 6, negative 1, negative 1. And I have a matrix. My guess is this is not what Sean did with you guys, right? Or whoever you happen to have.
Not at all, and I'm a little bummed.
But don't get mad at Sean, okay? By the way, Sean and I are opposites. Have I told you about that? I have a higher level degree in math, and I have a minor in chemistry. And Sean has a higher level degree in chemistry, and he has a minor in math. So he definitely knows his math. He didn't like skip it because he doesn't know matrices. He knows matrices. He skipped it because he can't assume you know matrices. So then I RREF. And when I RREF, this is what I get. Okay, I pop this into a computer, very simple. Can you trust me that that's what I did? So again, it's a lot of typing, but it's not hard. Okay, and you can do it by hand too. It's a pain in the butt, but you could do it by hand. It's not that bad. But computers do it very nicely.
Did
And this
you
is what
say
I
you
get.
F'd it?
Yep, I RREF'd the matrix in a computer using SimpleLab. And again, if you just Google search RREF symbol matrix, whichever one, they'll all work if they're done right, you know. All right, now I can't. So what are my free what's my free variable and what are my pivot variables?
You don't have any free variables.
Guess again. Remember, this is not an augmented matrix. This is a matrix.
The actual elements themselves are the free variable.
Which one?
Oxygen?
Yeah, oxygen. Oxygen. Because we have a pivot here in this first one, a pivot, a pivot, a pivot for all four of these ones. And those are the first four columns, which are sorry, not oxygen, E. Sometimes I get suckered into saying yes. Sorry about that. It's E, not oxygen. E doesn't stand for oxygen. It's water, actually. So the free variable is water, H2O. Because each variable is not an element. Each variable is a molecule. Does that make sense? So water was E, which is the last column, and that's not a pivot variable. Do you see that? All right. Now, you could let it be 1, but there's a problem. You don't do that in chemistry. What's the problem with letting it be 1?
Then you get like fractional coefficients and
right, and you're not supposed to get fractions when you do this. So what you do is you let it be the least common denominator. So what's the least common denominator of all these fractions?
4.
4. Okay. Least common multiple is what I meant. Least common multiple. So of the fractions. Greatest common. So least common multiple of the denominators. Okay. So I let it be 4. And if I let it be 4, then remember this is A is 1/4 times E. And if E is 4, A is 1. And there's a 1. And B is equal to E, so B is 4. C is equal to 1/4 E, so that tells you C is 1. And D is 1/2 E. 1/2 times 4 is 2. And then we said E was 4. So now we take this 1, 4, 1, 2, 4. That's our answer for A, B, C, D, and E, and there's our balanced equation. Isn't that pretty? And this is foolproof. This always works. Okay. This will always work. And if they give you a trick question that can't balance, what's going to happen when you try this?
It won't work.
What's going to happen in the matrix stuff?
You won't be able to find the RREF.
You'll find the RREF, but there's some. But what's going to happen is you're going to get a row that has a non-zero number. You're gonna end up with zeros on the bottom and non-zero at the end, exactly. Okay, and there's going to be a problem. Okay, but it turns out that's only with trick questions, so trick questions shouldn't happen. Because you always get a balanced equation. And hopefully Sean never did that to you, right? Okay, because it always works. Okay, any questions on this? Okay, again, if he gave you a trick question, what you're going to end up with is you're going to end up with all zeros. You're going to get only the trivial solution, and that doesn't count for balancing, by the way. Because it is true if I let A, B, C, D, and E equal 0. If I start out with nothing and you don't do quantum physics, you end up with nothing. Isn't that true? That you learn in chemistry, right? I put a disclaimer about quantum. Any questions on this application? Okay, now for the next application. And now we're looking at a circuit. Have you guys all seen a circuit diagram that might look something like this?
Yeah, this is Kirchhoff's law.
Yeah, I mean, this isn't Kirchhoff's law. We're going to use Kirchhoff's law.
Well, yeah, it's a circuit that you would use Kirchhoff's law to find.
Yeah, this is a circuit diagram. It's not a law, it's a diagram. But what we want to do, if we want to find out what I1, I2, and I3 are, and you all said you've seen this before. Okay, I1 in a word, what does I stand for?
Current.
Current. Okay, so if we want to find out the currents in each of these little curves, then we're going to use Kirchhoff's law. Okay, and in particular, we're going to use a loop law. Did you call it loop law in chemistry?
This was in physics. I think we called it
in physics.
It was like the loop rule of Kirchhoff's equation.
Law.
Equation. Yeah, same difference. Yeah.
Yeah, the rule of law doesn't matter, but it's loop. Yeah, so we're going to use the loops, and the idea is how many loops are there that you need? Do you guys know? You might have got this in physics. I'm not sure. How many loops in this picture?
There's 3 loops. Wait, no, 4, because the broader
Okay, there's 3 necessary loops. There's a lot more loops. Actually, there's more than 4. I think there's 6, but there's 3 that are necessary. So you only need to worry about a loop if there's no loop within the loop. So I have this loop here on the top left. I have this loop here on the top right, and I have this loop here on the bottom. I don't need, for example, this loop that does all the top. Do you see that? That's a loop also, by the way. Or this loop that does all of the right. I don't need that because that has loops within loops. Or I don't need the loop that does the whole thing. Not necessary. You won't get it wrong if you have all these extra loops. but you're going to end up with just a whole lot of rows in your matrix, and it's going to be a pain in the butt to type it in the computer. Got it? So it's a whole lot easier to just do the loops you need, so you don't have to have extra stuff. So then what we do is we just take these loops. So let's do the top left loop first. Got it? Okay, if you do the top left loop, and notice that this guy, let's just start at this bottom left. It doesn't matter where you start. Going from bottom left to bottom right, notice that we have 2 I1. Is that clear? Any questions on that? Now, if I go from this bottom right to top right, what happens? The hint is there's a couple things going on. Any ideas?
You pass a resistor.
Yeah, I passed a resistor. So I did that here too. I had 2 and they were I1s, right? But what's going on here? And it's more complicated. That's the hint.
Current splits.
Yeah, you get 5 I2, but you also get a negative 5. 5 I1, and you also get a negative 5 I2. Because where I2 is going around like this, and it's going in this direction, it's going down and we're going up, and that's why it's negative. Okay, now you should have got this in physics. Then if we go from top right to top left, we're going to get a 3 I1, because that only has one current involved. We don't have an I1 and I2 like before. And then if we go from top left to bottom left, we're just going to have 10. Any questions on that? So now let's put that together, and we'll do all of them actually, but I wanted to spend time on the first one, and then hopefully all the rest of them you'll be able to handle. So we can say the top left is going to be 2I1 plus 5I1 minus 5I2 plus 3I1 is equal to 10. Because the loop law says that if you add up all the current, you get the change in the voltage. And that's all part of that V equals IR. You got that in physics, right? All right. What I did is I want you to tell me what the top right is. Let's see if you can come up with that. And by the way, we get 10. I'm going to do this because it's easier to type. We get the first row of the matrix is going to be 10, comma, negative 5, comma, 0, 0 because there's an I3 also. And then comma 10, which will be the augmented part on the other side of the line. So let's see if you can come up. And I don't know if I'm going to finish all of this because I think you'll get the idea if you know how to do this. So see if you can come up with the second row of the augmented matrix. So the first row was 10, negative 5, 0, and 10. And by the way, I got 10 because 2 plus 5 plus 3 is 10. That's where this 10 comes. I added up the I1s. So let's see if you can figure out what the next row using the top right loop. Figure out what that is. And the hint, this is going to have an I1, I2, and I3 in it. So there won't be any zeros. And just to make it easy, let's go counterclockwise. If you do clockwise, what you do is you're just multiplying the whole row by -1, which doesn't change anything because that's one of the row operations, elementary row operations. So let's go counterclockwise. So it makes it so the I2s are all positive. And there's a lot of I2s. Let's see, you can put in the chat box when you get it. I did it in my head. Let's see if you guys, you don't have to do it in your head, by the way. The hint is there's a lot of negatives on this one. Or at least there's some negatives. A few, couple. Okay, 16 I2. 16 I2 minus 5 I1 equals 12. You missed an I3 in there. So notice that when you move out here, you're actually going against the I3 current. Do you see that? And then Jacob, we have -5. Yeah, so -5 should be the first one. Okay. And then 16, that looks right. And then should be -1. Because if you're going counterclockwise, you're going against I3. Do you see that? And what about the constant?
Should be negative, right? Because we're going from.
Yep, we're
higher
going the
to
opposite
lower.
direction of the arrow. So it should be -12. So the next row should be -5, 16, and then -1, and then -12. Any questions on this? Okay, and I want to let you know, just so you don't like accuse me of like being so much different than the homework. This was copy and pasted from the book. It wasn't the one that was assigned, it was the one after that that was assigned, but basically they look like this. Because it's a lot easier for me to copy and paste because that drawing this picture is hard. Can you all be okay with getting the third row and figuring it out at that point with our REFing? Because I need to move on. And you get the idea?
Yeah.
Now, my guess is Kathy did not do it this way. Am I right? With the matrix. She probably had you do equations though, right?
I think she actually did use a matrix at one point.
Really?
Yeah. She asked us to ask Bruce about RREFing actually. So I heard that term before.
Yeah, because I don't think you get, because you really, this is the first time you learn about RREF. So that's neat that Kathy did that.
Although we used a computer to do all the RREFing.
Okay,
Bruce
which you
is
can
still the
do
principal from Alpha.
on application questions. I'll let you use a computer to do that. Again, I'm only going to have you do one by hand on a test. You know, one RREF, and I'm going to have you do one just because you should do one by hand. All the rest, I'm going to assume you can use a computer. Sound good? Sound fair?
Definitely.
Okay, now a bunch of very simple definitions, We don't have that much time, but we don't need that much time. The first one is if A is a matrix, then we write down A subscript ij, and usually don't put in commas because most people don't deal with matrices that are 2 digits. So if you have A1, 2, it'll look like 12, but it's clear it's not a 12 by 12 matrix. Does that make sense? So typically you don't use commas, you just do number next to each other, just easier. And that is the element in the ith row and jth column of A. Okay, this is not a hard definition, but it's a really important one. So here's a matrix. 2, -1, I'm reading the rows, 4, 0, 7, 3. Can you tell me what A31? And this is not 31, that's what I'm trying to say. I'm looking for a number. So it's A31.
7.
Yeah, A31 is 7, because it says, look at the third row, first column. The third row is this row here. Oops, I can't. Well, this row, I'll point to it. And the first column of that is a 7. Any questions on that? Do you agree this isn't some fancy thing? This is notation, and we're going to be using it all the time, so it's important I write that as a definition. Okay, so whenever I have A and there's a 2-digit number, it's not a 2-digit number, it's 2 numbers next to each other. Got it? Okay. Next, also really easy, is a square matrix is a matrix with the same number of rows as columns. And hopefully you all are convinced that the word square is probably a good word to use for this. Do you see the square in this? Especially if I highlight it. It actually shows you a square on Word. So, whereas if you had a matrix that was instead of, this is a 3 by 3 matrix, if you had a 3 by 5 matrix, that won't be a square matrix. It'll look like a rectangle, that isn't a square. Do you see that? Okay, I would say maybe 2/3 of all matrices we're going to be using in this class will be square matrices. So it's really important to be able to handle square matrices. So it's worth talking about the definition. There's not much to it. You could write down a 5 by 5 square matrix. By the way, there's always a fun one. Is that a square matrix? What I just typed?
Yes.
Yeah. It's a 1 by 1 matrix. It's fine to have 1 by 1. I usually don't do a whole lot of examples that are 1 by 1 because they're numbers. And they're not very interesting. But it is a matrix. It's a square matrix. So square matrices could be whatever, n by n, where n is a number, including 1 by 1, 3 by 3, 100 by 100, whatever. Any questions on a square matrix? Stop me, by the way, if I go too fast. I'm going fast on these easy. I consider these easy. Do you consider these easy? This is not going to make your head spin, or it shouldn't. Okay, next definition. Also really easy and very important. It's important to know what 0 is, right? Okay, so the M by N 0 matrix is the matrix with n rows and m columns such that Aij equals 0 for all I and j. Also a very easy definition. And here's an example. This is the 2 by 3 0 matrix, which would be different than a 2 by 2 0 matrix. So this is one of these weird cases that you're not used to, where there's lots of different zeros that aren't the same thing. And actually that happened last quarter. When did it happen last quarter? When were there different zeros? It happened a lot. I don't see y'all jumping in. All right. If you don't know, I'll tell you. Vectors. Right? There's a 2-dimensional zero vector. There's a 5-dimensional zero vector. They're not the same vector, right? So matrices also. Okay. If you have different dimensions, then it's a different zero. Any questions on the zero matrix? Do you agree it's easy? Okay, so zero matrix is going to be important, by the way. We're going to use it a lot for different things, you'll see. Okay, here's also another really easy definition. It's harder to write than it is to understand. So if we have two m by n matrices A and B, then they're equal. If they're equal, that means that Aij equals Bij for all I and j. Okay, that's a fancy way of saying you look at the matrix and you compare them, and the corresponding numbers are all the same. Okay, so for example, if I have the matrix, let's make up the matrix. Three, 4, 0, 1. And let's do another one. Okay, are those matrices equal? So not a hard question, by the way.
No.
No, they're not. Okay, because all of the entries must be the same. And notice that the 2, 1 entry are not the same. Because A21 is 0 and B21 is 1. And if anything goes wrong, they're not equal. Got it? Any questions on the definition of equal? Okay. Just note, by the way, a 2 by 2 matrix is never equal to a 3 by 3 matrix. So if they're in different universes, they can't be equal either. Is that clear?
I have a question for you.
Sure.
If you have two matrices that are not the same in this sense,
Are not equal.
are not equal, is it possible for two RREF matrices to be equal and not look like this?
Absolutely. So remember the word we use for it. We don't use the word equal. What do we use when it's RREF the same? Starts with an S? Or E, sorry, starts with an E. But not equal?
Equivalent?
Yeah, equivalent.
Yeah.
Yeah, so we call it equivalent. So we call those matrices equivalent when you RREF them and you get the same. And equivalent is not the same thing as equal, that's for sure. Does that make sense? Yeah, so make sure you note that those are different words, equal and equivalent. Okay, so again, this isn't supposed to be tough. Equivalent is harder because you actually have to do stuff. But if I ask you if two matrices are equal, you shouldn't take more than a half a second to tell me if they're small enough matrices. If it's a million by million, good luck. And one of the numbers might be different, go find it. That's why you write computer programs. Any other questions on this one? Do you agree? We have a lot of definitions today, but nothing too bad. Okay, now comes something really important, and that is arithmetic. Okay, and you should know, since you were maybe 5 years old, or like me, 2 years old, that arithmetic is important. Do y'all agree? And third quarter, we talked about arithmetic of vectors. Remember that? Now we're going to do arithmetic of matrices. Okay, so let's get the definitions down. So I'm going to start out, when you learn arithmetic, you may not remember, but when you learned arithmetic, which might have been in kindergarten or earlier, what's the first kind of arithmetic you learned?
Addition and subtraction.
Yeah, well, the first one was addition. Okay, if you have a child, you know that. Otherwise, you were too young to have that memory. But trust me, that'll happen. Okay, if you have a child. And addition's first, and we're going to do addition first. And the wonderful thing about addition is just what you would guess it is. And that is, so let me tell you the definitions formally, and then doing it is easier than reading the definition. And that says that if we want to add A and B, then the ijth component of A plus B is the ijth component of A plus the ijth component of B. So in simpler words, if you want to add two matrices, you just add the components. Okay, but you can't always add matrices. So I gave you an A, B, and a C. So I have A plus B, A plus C, and B plus C. Do all those make sense or not? And if something makes sense, which one makes sense and which don't make sense?
A and C makes sense.
You mean let's call it part 1 and part 3. Is that what you mean? Or you mean A plus C?
A plus C.
A plus C. Yeah. A plus C makes sense. A plus B is not possible. You can't add those. And B plus C is not possible. You can't add those. They're different kind of matrices. And if they're different dimensions, you can't add them. Same with vectors. If vectors were different dimensions, you can't add them, right? So we can add A plus C. And it's not that hard. Let me do some copying and paste so I don't have to do the whole grab a matrix out of the matrix equation editor stuff. And let's just do it. A plus C equals, and you just do it the easy way. You have 1 plus 3 is 4. We have 2 plus 0 is 2. We have 4 plus -2 is 2. We have 3 plus -1 is 2. We have 0 plus 8 is 8. And we have 2 plus 5 is 7. Do you all agree that's easy? A little tedious, but that's it. And the others you can't do. By the way, what about A plus A? Can you do that?
Yes.
Yeah, and
Yeah.
always. You can always do A plus A, no matter what dimensions A are. Because A and A is always the same dimensions, right?
Couldn't you just say A times 2 though in that case? Or
We'll get there. We'll get there. Yeah, but you have to be careful. So it turns out addition has all the properties you like. So A plus C is C plus A. That works. No problem, right? Do you agree? But I'll let you know, you're gonna be pulling your hair out in a little bit. So I'm gonna, is it okay if I don't do an example of subtraction? Same thing, except you subtract instead of add. Are you okay with that?
yeah.
Okay, so that's one arithmetic, or that's two arithmetics, I guess, addition and subtraction. Another one, and this is important if you think about vectors, and that's scalar multiplication. Do you remember with vectors, there was scalar multiplication? You can multiply a number times a vector. Same thing with matrices. And with matrices, it's the same idea as with vectors. So the definition is if K is a constant and A is a matrix, then if you take K times A and you look at the ijth component, that's the same as K times the ijth component of A. Okay, it's a lot harder to say than to do. So we know A, if A is, I'll use the same A, 1, 2, 4, 302. And then how do I get 5A? What do? The hint is it's easy.
Multiply every entry by 5.
Yeah, multiply everything by 5. So you get 1 times 5 is 5, 2 times 5 is 10, 4 times 5 is 20. It's tedious. 3 times 5 is 15. 0 times 5 is 0, and 2 times 5 is 10. And there's 5A. Any questions on that? Okay, now the good news is that the properties that you learned, like the distributive property, for example, still works when you're talking about addition, subtraction, and scalar multiplication. Got it? But only addition, subtraction, scalar multiplication. Stop there. All right, what haven't we done yet?
Adding, subtracting, full matrices together. Or,
No, we did adding, subtracting.
Multiplying matrices.
Multiplying matrices. And do you remember when you had vectors? That was a lot more complicated, wasn't it? You had a dot, you had a cross. It was messy, remember?
Yeah.
All right. With matrices, it's also messy, and it's not what you want it to be. And when I say want it to be, it's not just multiply the numbers out and you get it. And in fact, you can't even multiply when they're the same dimensions sometimes. So here's a definition of multiplication. Let A be an M by N matrix and B be an N by R matrix. Very important, notice that the number of columns of A is the same as the number of rows of B. And let VI be the ith row of A and WJ be the jth column of B. Then ABIJ is VI dotted with WJ, where it's truly the dot product. Okay, if the number of columns of A is not equal to the number of rows of B, then it's not even defined to multiply. So let me ask you, I have 3 choices, AB, AC, and A squared. Okay, which ones can and which ones can't be done?
AB can't be done, but AC and A squared should be able to be done, I think.
Okay, not quite. Good try though.
I think AC can't be done.
Okay, it's actually the exact opposite of what the first person said, and that is, let's look at AB. Okay, well, AB, we have how many columns in A? How many columns?
3.
3. How many rows in B?
3.
3. So AB can be done. Do you see that? Any questions on that? How about AC? How many columns in A?
3.
How many rows in C?
2.
2. They're not equal. You can't do AC. How about A squared? That would be A times A, by the way, by definition. Can you do A squared?
No.
No, because the number of columns of A is not equal to the number of rows of A. So you can't even square a matrix unless, what kind of matrix can you square? The hint is, I just said it, kind of.
A 1-by-1 matrix.
In a word. One word. A square matrix, yeah. A square matrix can be squared. You can't square a non-square matrix. Okay, so I'll let you know, by the way, you could even take E to a square matrix. And that's just weird, right? Because you do it with power series. And you can take any power. I'm not going to do that now. Don't have time. We only have a few minutes left. So, but we can do A times B. So let's do A times B. So to do A times B, first thing, what I'm going to end up with, Notice that there again, if you look at the number of columns of A, we have 3. The number of rows of B, we have 3. Do you see that? The number of rows of A, I have 2. The number of columns of B, I have 2. So if I do A times B, I'll get a 2 by 2 matrix. So let's get that 2 by 2 matrix. I wonder if I have one up here somewhere that I can grab to copy and paste. Yeah, there's one. I just want to copy and paste it. It makes it easier. In Word, at least. It's kind of a pain to get a new matrix. Okay, so I could do A times B. Let's change these numbers. Okay, so A times B. Well, the first thing is I'm going to take the first column of B, or let's say the first row of A, and dot it with the first column of B. And I get 3 plus 10 plus 8, which is 21, right? So the first entry will be 21. The 1, 1 entry will be 21. Okay, now let's take the first row of A with the second column of B. I get 1 minus 2 plus 16, which is 15. Okay, now let's take the second row of A with the first column of B and dot those. I get 9 plus 0 plus 4 is 13. And then I'm going to take the second row of B with the second column of B, and I get 3 plus 0 plus 8, which is 11. Any questions on how I got that? So AB is a 2 by 2 matrix, by the way. Okay, and that's it. Okay, by the way, B is A times B the same as B times A? Do you have commutativity? Absolutely not. A times B was a 2 by 2 matrix. B times A will be a 3 by 3 matrix. Won't even be the same dimension. Not even the same universe. Can't be the same. So A times B is almost never the same as B times A. So beware. Beware about anything that you're using in algebra for multiplication. How about if A times B equals C? Can you divide by A? And just say that B equals C over A?
No, I don't think so.
Sounds good in algebra, but there is no such thing as division. We don't have division. You can't divide. That doesn't work. You can't even say divide by A. Those words don't work. Got it? So beware. Okay? How about if A times B equals a 0 matrix? Does that mean A is 0 or B is 0? True with numbers, right? If A times B is 0, then A is 0, B is 0. If A and B are numbers, what about matrices? And the answer is no. And you learn that from vectors, by the way. Same thing with vectors, because you can have orthogonal vectors, perpendicular vectors, where neither is 0, but you get the 0 when you dot product. Has something to do with that. Okay, I have 1 minute, and that's all I need for this. And that is a transpose. So here's the definition of the transpose. It's really easy. If A is an M by N matrix, then the transpose of A is defined as A transpose IJ is AJI. So it says just switch. So what it means is that rows become columns and columns become rows. So I start with a 2 by 3 matrix. I'm going to end up with a 3 by 2 matrix. So I wonder if I have a 3 by 2 matrix. I can copy and paste and change the numbers. So notice the first row of A is 1, 2, 4. So the first column of A transpose is 1, 2, and 4. The second row of A is 302. So the second column of A transpose is 3, 0, and 2. Any questions on the transpose? Do you agree that's easy? Much easier than multiplication? Do you think transpose is important? Think it comes up? Yeah, surprisingly everywhere. Okay, in like, I'd say 90% of all like big applications of matrices, you're going to see transpose. Just let you know, it comes up a lot. Today is just mechanics, and we'll get into all the applications later, and transpose is really important. But we're out of time, so I'm going to stop the share. And I am going to stop the recording, but thanks a lot.